we now come to one of the most interesting parts of mathematics regarding all of introductory physics. And this is the frequencies of small oscillations for generic potential energy functions. Okay, so the entire idea of having a generic potential energy function is if your potential energy function has a local minimum. It doesn't even have to be a global minimum. It can be a local minimum. As long as you have a local minimum, you have the potential for oscillations, because if I put a particle right at this minimum and then displace it slightly up the potential, then it'll just roll back and forth. And we will have, it'll roll back and forth. And when I say roll back and forth, I mean in the potential energy space. It doesn't have to roll. It could be moving back and forth on a spring. But as far as the potential energy function is concerned, it's just going to keep rolling, sliding, if you like. It'll just keep sliding between these two endpoints. Okay? And so this is what your oscillatory motion is. So as long as you have a local minimum, then you have the potential for small oscillations, right? So we start with the general result from calculus. Okay? Functions can be approximated by a polynomial chain in the region of a local extrema. We call that local extrema x naught. And so the idea here is that no matter what your function is, you can approximate any function with a string of polynomials. Where your A, B, C, D, and E are some appropriately chosen coefficient. Okay? So the idea is, can I find the appropriate polynomial to represent the function in the region, in this case, of my local minimum? Okay? Now, the small oscillations will only work for local minima. Okay? If I had a local maximum, I wouldn't get oscillations because the object would not come back to the original equilibrium point or move past it. It would escape. Okay? So a local maximum, just for context, if I have something like this, where I have a function with a local maximum, right? And I put my particle right here. If I displace it slightly this way, it just continues down here. It never comes back. Or if I displace it this way, it comes down here and it never comes back. So local maxima do not give you oscillations. Okay? Local maxima do not give you oscillations. Only local minima do. All right? So here is the result from calculus. Now, I'm not going to derive or justify this. All right, we're going to state it, and then you will go through this in your calc class, Calc 2 specifically, in much more detail than we're going to cover here. We're just going to give you the ability to use this result. Okay? So we're going to apply what's known as a Taylor series. Okay, so in the region of your local minima, and here we have our local minimum, right? And let's actually erase the particle and the arrows, so it's a little bit easier to see exactly where that minimum is. So if this local minimum is designated as x naught, okay, so this point right here, we're labeling as x naught. Then your Taylor series says, in the region surrounding that point, I can approximate my function, in this case our potential energy function, by the sum of my function written like this. Okay? So let's break this down. This is not an exponent. Okay? But this is an exponent. And n starts at 0 and goes up to however high you would like. Okay? So the idea is you evaluate your first derivative, second derivative, third derivative, fourth derivative, etc. You find the local maximum or local minimum. In our case, this is going to be a minimum. And then you plug everything into this formula. Okay? So u to the 0 is the 0th derivative. Which is just the function. u1 is the first derivative. u2 is the second derivative. Etc., etc., etc. Okay? So, why are we doing this in the first place? Well, remember that Hooke's law is valid for quadratic potentials. Right? So the idea is that if you have a local minimum, then if you zoom in close enough, you'll eventually find something that approximates a quadratic. And once you have the quadratic, then you have Hooke's law. And you can then say something about the oscillations that would occur in that region. Okay? So that's why we are doing this. Okay? Now, let's see how this works in practice, because this is very esoteric at this point in time. Okay? But, so the steps are, okay, so step 1, find the equilibrium point. Step 2, evaluate derivatives. Step 3, plug into Taylor expansion. Step 4, read off the spring constant. Okay, now This is going to be a fairly complicated process to show step by step. Okay, so bear with me. But the punchline is that once you familiarize yourself with this, you'll be able to get the spring constant, the effective spring constant, extremely easily. And then step 5, this is assuming you know your mass, then your frequency is just 1 over 2 pi square root k over m. Okay? So our job is to determine k from this expression. Now, believe me when I say, I understand if that makes no sense at the moment. But bear with me, okay? Bear with me and we'll find out what's going on. So, here's the thing, right? U of x can be approximated by the summation of n equals 0 to infinity of the nth derivative evaluated at the equilibrium point times the quantity x, which is your variable, minus your equilibrium point. So this term is just shifting the origin. Okay, this term is just shifting the origin to your equilibrium point. Divided by n factorial. So what this does, if I write this out term by term, so the 0th derivative evaluated at the equilibrium point divided by 0 factorial, okay, this is just going to be a constant number. Okay? Because all I'm going to do is I'm going to plug in the equilibrium point into my function, evaluate that, and then divide that by 0 factorial, which is 1. And then this is going to be, whoops. Explicitly, we should draw or write out the fact that this is x minus the equilibrium position to the 0th power, but this is also 1, so it also goes away. Anything to the 0th power is 1, so that's fine. So then we have the first derivative of u evaluated at the equilibrium position divided by 1 factorial times x minus x naught plus the second derivative of u evaluated at the equilibrium position divided by 2 factorial times x minus x naught squared. Okay? Now, this goes into higher order terms, but the entire idea is this term right here. 2 factorial is equal to 2. So 1 over 2 factorial is the same thing as 1/2. Then we have the second derivative of u evaluated at the equilibrium position is a constant number, and x minus x naught squared is the same thing as a displacement squared. So this term has the form 1/2 times a constant times a displacement squared. And this is your potential energy of a spring. We'll see why the first and second, well, let me put it this way. We'll see why these two terms drop out of the calculation And once you are at the squared term, as far as oscillations go, you don't need any of the higher order terms. You just need this term right here. Okay. So let's do an example. All right, let's come back up here and let's look at this example right here. Say I have a potential energy function that looks like this. Okay. I have a potential energy function of 2 joules times cosine of 0.5x. And I'm looking at this function from x equals 2.5 to x equals 10. And this is what's plotted right here. Okay. So this function is okay. The blue line is that function right there. So let's go through our process. Find the equilibrium point. Now, if you haven't gone through this kind of process in calculus yet, your equilibrium points are where your derivative disappears or where your derivative is horizontal. I should say the derivative is 0 where your slope is horizontal. Okay, so that means that the slope of my function right here is going to be 0 right at the bottom of that minimum. Okay, so what you do is you take the derivative of your function to get the slope, and then you set it equal to 0 and solve for x. Okay, so let's at least start the process here. Okay, so step 1, take the derivative of u. And by the way, superscripts that look like this or like this or like this that we refer to as derivatives, these are what we call primes. So u prime, u double prime, u triple prime, that means first derivative, second derivative, etc. Okay, so the first derivative of u, well, actually, let's rewrite the function down so we're not just constantly flipping back and forth between slides. So if u of x equals 2 joules times cosine of 0.5x, then u prime, or the first derivative, is 2 joules, stays where it is, but I get a 0.5 out front. And this is inverse meters to make the cosine argument unitless. And the derivative of cosine is negative sine. Okay. And then we set this equal to 0, and first things first. Okay. Negative 2 times 0.5 is just 1. Okay. And we need this to equal 0. And where is this going to equal 0? Well, sine goes to 0 at integral, or I should say integer values of pi, right? When pi, well, let's put it this way. Sine of y equals 0 when y equals 0 plus or minus pi plus or minus 2 pi plus or minus n pi, where n is an integer. Okay? And if we go back and look at our range, okay, when x equals 2.5 and x equals 10, 0 is outside that range, right? So we can't set this equal to 0 and solve for x. We need to set it equal to pi, because pi is 3.14 and 3.14 is between 2.5 and 10. So what that means is we're going to set 0.5 x is equal to pi, and that gives x is equal to 2 pi. And if you think about it, that should make some sense. And if we look back at this graph, that's exactly what we find, right? 2 pi is about 6.28. And the bottom of this graph is, even just visually, you can tell that it's at least really, really close, right? So it's not a formal proof, but, the eyeball test, but it should agree with what you get mathematically, right? Okay, so our x naught, our equilibrium position is 2 pi. So we found the equilibrium point. Step 2, we're going to evaluate the derivatives at that point. So the first derivative, which we just found, it's negative 1 times sine of 0.5x and so we evaluate that at the equilibrium position. Actually, let's do the 0th order first. I really apologize. Let's do the 0th order first. It'll make more sense. Okay, so our 0th order coefficient is going to be 2 joules times the cosine of pi, but the cosine of pi is negative 1. So our function evaluated at the equilibrium position is going to be negative 2. Okay, and if we're very careful, we keep our units here. Now let's evaluate the first order derivative at x equals 0. Now, we're going to do this one explicitly, but I'll tell you the general result that should always happen with this particular term. And that is, this is going to be negative 2.0 joules. Hang on. Let's make sure we got this right. Yeah, negative 1. Sine of 0.5 times 2 pi. But the sine of 0.5 times 2 pi is the sine of pi. The sine of pi is 0, so this whole thing goes away. And if you think about it, that should make some sense, because you found where the slope is 0 and the derivative is the slope. So u prime evaluated at your equilibrium position will always be 0. Okay? Now, that won't necessarily always be true when you're doing generic Taylor series, but when you're doing equilibrium position analysis, that will always be true. Okay? And we evaluate the second derivative So we evaluate the negative sign stays. And my coefficient of negative 1.0 stays. The derivative of sine is cosine. And I'm going to leave a space. You'll see why here in just a moment. And I get another 0.5 out front. Inverse meters. Okay, so this is going to be negative 0.5 cosine of pi, but cosine of pi is 1, negative 1. So negative 1 times negative 0.5 is 0.5. So this is 0.5 joules per meters squared. Okay, and I really should be explicit. We're evaluating this at the equilibrium position, so this is u double prime at x naught. Okay? Now you can compute the higher order terms, but we're not going to do that because we only need these first three. So u, our original function, is now approximated by these three terms. Okay? So we've found u naught, which is of course just the function, and we evaluated that at the equilibrium position, so that's negative 2, plus 0 plus 1/2, because remember, we have the 2 factorial, which carries a factor of 1/2, times, well, actually, yeah, let's just continue, and then we'll draw the appropriate comparisons. Okay, so our potential energy function looks like this. All right, and so this is u naught, or u0 evaluated at x naught over 0 factorial. This is u to the first, or u prime, x naught over 1 factorial. And this is u double prime evaluated at x naught times x minus x naught squared over 2. Okay? And so what I've done is I've plotted this function in Python and overlaid it with the original function. So this is u of x, our original u of x. This is the Taylor series u of x. And notice how maybe from about right here to maybe about right here, at least at this scale, the yellow lies right on top of the blue, right? So that tells us that this is a good approximation. For our original function. And that means if I place a particle here at the equilibrium point, and then I displace it slightly this way, it'll just oscillate back and forth. Okay? So we're nearly there. So what that means is that, okay, so this term is constant. And remember, you can adjust your zero for your potential energy wherever you choose. So you can, shift your potential energy up or down however you like, and it doesn't change the physics. So you can arbitrarily set this term equal to 0. With impunity. Okay? This term is already 0, and if you you might have realized this before, but this is the force. Because your force is equal to the negative of your first derivative with respect to position, I should say the force sans minus sign. But the entire idea is at equilibrium, the force is equal to 0. So whether you want to view this term as being 0 because it's the derivative evaluated where the slope is 0, or that's the mathematical way of viewing it, or from the physics point of view, at equilibrium, the force must be 0, this term drops out. And so we're left with this surviving second term. And as a result, my potential energy function can be approximated as 1/2 times 0.5, in this case it's joules per meter squared, times x minus my equilibrium position squared. This has the form 1/2 kx squared. So k is your second derivative evaluated at your equilibrium position. Oop. All right. So k is your second derivative evaluated at your equilibrium position. So if you know m, if you know your mass, then the frequency of oscillation is given by 1 over 2 pi square root k over m, or 1 over 2 pi square root second derivative of u evaluated at the equilibrium position over m. So all of this is a justification for why you only need to find the second derivative and evaluate it at the equilibrium position. So you do need to find the equilibrium position, but then all you need to do is take the second derivative. You don't even have to worry about the first derivative. You don't have to worry about the third derivative. And you'll notice that here in this picture, if we're restricting our discussion to between, maybe 5 1/4 and 7 1/4, maybe close to 7 1/2, whatever the case may be, this is a good enough fit that I don't even have to worry about the higher order terms, right? So that's why if you can find a small enough region where your function is approximately polynomial or quadratic, that's as high as you need to go, and that automatically gives you a Hooke's law form for your potential energy function. Okay? So all we need to do is find the second derivative, evaluate it at the equilibrium position, and then plug it into this formula to find the frequency. Okay? So this is your effective spring constant. Okay? Your second derivative of your potential energy with respect to, or evaluated at the equilibrium position, is your effective spring constant. So, in our example, U of x is 2 joules times cos of 0.5x. If the mass of the particle is, I don't know, let's say half a kilogram. Okay, so we want to find the angular frequency, the frequency, and the period. Well, the angular frequency, okay, so let's start by finding K. Now, we've already almost done this, right? So K for us, I put it over here, didn't we? K for us is going to be 0.5. Is that correct? Yes. Yeah, because it's right here. Right? So K for us is 0.5 joules per meter squared. Okay. And joules per meter squared, joules is force times, or newtons times meters. Which gives you 0.5 newtons per meter. Okay? So these are the units of your spring constant. These are units of a spring constant. And that's worth 3 exclamation points. Right? So we found K. We know that the mass is 0.5 kilograms. So A, the angular frequency, is the square root of K over M. Or the double prime evaluated at the equilibrium position divided by M. So this is going to be 0.5 newtons per meter divided by 0.5 kilograms. So this is going to be 1 radian per second. Okay? So our angular frequency, if I have a particle of half a kilogram in this particular type of potential energy well, then if I displace it from its equilibrium position just slightly, it will have this angular frequency for its oscillations. B, the frequency, is 2 pi, or that divided by 2 pi. And this is why your rads cancel out. Even though they're unitless, your 2 pi is technically in radians. So 1 divided by 2 pi will give us 1 divided by 2 divided by pi, 0.159. Hertz, or cycles per second. Okay, so this is going to go through around 16% of a cycle per second. Okay, and then C, the period, okay, so this is going to be 2 pi. And if k over m is 1, then m over k is 1. So this is going to be 1. And this is going to be seconds per radian. And the radian is going to cancel out with the radians from 2 pi. And so this is going to be 6.28 seconds. So this particular particle, if placed in this kind of well, it will take 6.28 seconds to complete one full oscillation cycle. Okay, so to sum up, okay, the punchline is that, number one, find your equilibrium position, and then 2, evaluate the second derivative of your potential energy function evaluated at that position. And then your spring constant equals that. Okay? So then when you have that, you can just use Hooke's law. Or the results from Hooke's law, really. Man, the pad seems to want to connect those lines. There we go. Whoops. This should be reversed. And once again, we need, there we go. Okay, so this is how you find the frequency, angular frequency, or period of oscillation for a particle that is not in a pure quadratic. Okay, if you displace it, if it's in a local minimum and you displace it small enough, you can find the parabola that approximates that local minimum. Okay, so that's the basic idea. Okay, so I know that was fairly mathematically heavy, but I hope you followed everything. And if you didn't follow it explicitly from the beginning, watch this video a couple of times, but do take away these sum up points. Okay, these are the things to take away. Even if it's not incredibly clear why this works yet, it will become extremely clear when you do these several times in Cal 2. But for the moment, we just need to use these results. Okay, so that is oscillations for general potential energy functions. When your oscillations are small enough, or your displacements are from equilibrium are small enough. Now remember, this has to be for a local minimum. If you have a local maximum, you will not get oscillations. Now, so an example of a equilibrium or a stable equilibrium, right, would be something like a spring with a mass or a pendulum. Okay, when I displace those and the spring starts oscillating, it's trying to push the mass back to the equilibrium point. It's just that there's too much kinetic energy when it crosses the equilibrium point, so it keeps going. Same thing with the pendulum. When I pull a pendulum back, it's trying to get back to the equilibrium position, but when it gets there, it has too much kinetic energy, so it just continues through until all of that kinetic energy is exhausted into potential, and then the cycle just goes back, and it just reverses direction each time. And so it just continues to swing back and forth. An example of an unstable equilibrium, right? So like that balancing point. Think of if I have an unstable equilibrium potential energy function. Okay, then the peak of that point is your equilibrium point. That's a local maximum. But if I displace my particle either way, it will accelerate away and it won't come back. So one way to kind of visualize this is imagine, let me see if I can draw a really flat plane here. Not really, but you'll get the point here in just a second. Imagine I have a pencil balanced on its tip. Okay, and let's say this is a number 2 pencil, because why not, right? I can absolutely balance my pencil on its tip. There's no law of physics that says I can't. It might be extremely hard to do, and it might take me a while to actually do it, but there's nothing that says I can't balance my pencil on its tip. The point being, if I give that pencil, once it's balanced, if I give that pencil any sort of tap, it is going to fall over. It is not going to lean one way and then come back to the equilibrium position and start oscillating. It is just going to, let's say I give it a little bit of a tap this way, just an ever so slight tap, and the pencil falls over. Okay, so that is an example of an unstable equilibrium. So this is why you need stable equilibria to have oscillations. Okay? If you have an unstable equilibrium, if you slightly disturb that system, it will run away from the equilibrium point, not toward it. Okay? So you need to have a, in the words of calculus, you need to have a concave up potential energy function. Okay, you need to have a positive parabola with a local minimum. It doesn't have to be a parabola, but something you can approximate as a parabola using these Taylor series that we went through. But you have to have a local minimum. Okay, cannot have a local maximum. If you have local maximum, this is unstable. Okay, so stable equilibrium, local minima only, or global, but some sort of minima. And because it's a minimum, I can then draw this parabola that approximates at least a portion of that. Okay? So that is how you find the frequency of small oscillations for a general potential energy function. As long as there's a local or global minimum, you can do this process and you'll be able to find the frequency assuming you know the mass. Okay? All right, we will see you next time.